Okay, like that, it's better. Okay, so I will not give the full presentation of the application of artificial intelligence to geophysics, as Leonard has first considered to do, but I will go to a particular application that I think is of interest and also is conceptually interesting. And so it's a work that was by Leonard and René, who has also a poster here, and the colleagues from Rice University. And so the context of this study is the one of the slow sleep events, and because it's an interdisciplinary school, I have to tell a word about that. And the word is very simple. You know that the largest earthquake occurs on the subduction, and we have this, in the past, this classical view that we have the oceanic crust that is passing beneath the upper crust here, this other crust, and during a long period, there is a zone that is blocked here in red, and so the plate motion produces an elastic deformation of the upper crust here. And what we measure during this long period is this motion toward the continent, in most of the case, that we can measure by geodetic techniques that are due to this motion. And one day, after a long stress accumulation in this region, a large earthquake occurs, and it's the place where you find the mega thrust event, the very large event. So, if we look at the horizontal displacement that is here, what we expect is to see a continuous motion toward the continent up to the point where a large earthquake occurs, and then it will restart. It's what we call the seismic cycle. And the idea that it's roughly monotonic during this period without great earthquake. And this has been the base for seismic risk assessment for a long time. But okay, now we can look at this period here in Mexico, in a time where there is no particular big earthquake. So the subduction is here, so it's the Pacific plate that is going beneath beneath Mexico, and this is one of the GPS stations, and you see that actually it's extremely active. It's not at all monotonic. It's going toward the continent. That means that it's blocked, and then at a point it's go back, and we start to go in the north direction, and to the south, and to the north, and here to the south. And this geodetically discovered event are silent earthquake. That is big zone of sleep on the subduction plane. And for example, here, this one has a magnitude that we can compute. We know the sleep and the extent, and the magnitude is 7.6. That means that it's a very large earthquake. And this earthquake were completely ignored by the seismologists because there is no radiation. Why no radiation? Because it's slow, and if the sleep is occurring at speed that are much lower than the wave speed, there is no radiation, no seismology, and so we were completely ignorant. And we were ignorant, and it has been discovered by the geodesists, but you see that it's a very complex feature, and in the past it was very difficult to detect because you have only discontinuous measurement. And so, yeah. Sorry? Oh, no, it's centimeters. Because you are not measuring the slip, you are measuring the deformation of the crust, the elastic deformation of the crust. No, it's, oh yeah, the time scale is missing. So I will do I will do exactly as Matthias. It's more than that, but It's actually, it's, I'm doing like Matthias. You know, Leonard is really... No, actually it's several years, because this period here is about 4 years. Yeah, it's every 4 years in this region. And so this is very important, because it has been, it has completely changed the perspective about this process when we discover that there are missing earthquakes, hidden earthquakes, that the seismologists completely ignore. So all the balance of the formation was wrong. So it's very important, and of course here we see it, and we will study this region because it's so large that it's easy to see on the GPS data, but maybe it exists everywhere on every fault, and it's just a fundamental aspect to study. So I need to say one word about geodetic data, and here you see in blue the daily displacement in meter, so this -3, so this is millimeter. And this is the daily displacement. And this is just to show you the variance, the uncertainty of the geodetic short time measurement. It varies a lot, and this dashed line is actually the mean displacement. That you see the variance is much larger than the mean. So it's in the same time, this type of data, the ground truth of what happened as a deformation in the Earth, and in the same time, we can relate only on cumulative slip, because short time slip are by far too noisy to be used. Okay, so we have this information, and we have also another information that could be the seismogram recorded during this period. Nikolai already told you about that, and you have a diversity of signals that occur, that are the regular earthquake, the tremors. The tremors are maybe the summation of a very large number of low-frequency earthquake, sometimes very low-frequency earthquake that has been detected also in this region. So all a diversity of signals. And so for already some time, people realize that there is a correlation between this low slip event and some classes of this event, and mostly LFEs and tremors. So what we have to just to consider, for example, here, the past studies, always in the same region. This is the places where you observe tremors and LFEs. And this is, you know, now you have the time here. It's for one of these slow slip events. And the blue periods correspond to the period with large LFE activity. But when you look at that, you have the impression that it's a continuous motion during the slow slip event. If you use this information, that you have period of very high seismic activity, and you separate all this information based on that. So, and then you cumulate the displacement that you observe when there is no high rate of LFE, and separately you cumulate the displacement for high rate of seismicity. And what you observe here, that during the slow slip event, when you have LFE rate that is low, this is a period of loading, and the motion is toward the north. That is, the system is blocked on short time scale, and so the crust is pushing to the north. But in the same time, all these blue lines correspond to a very rapid motion in the other direction. You cannot see it on a single time scale, I mean days or something like that, but when you accumulate, it's very clear that there is this type of behavior. And that shows you that the classical, very smooth information here will not be enough to understand this physical process, because they are also acting on a much smaller time scale. Okay, so what we did before is take seismogram, making detection, explicit detection of particular event, and then we build catalog. And from the catalog, we make this type of decomposition. And this is an arbitrary choice of what is low and high, and so on. So there is no real definition, even of the events that are in this catalog, definition of tremor. And there is a decomposition threshold. So it's really too brutal and arbitrary. So what we would like to do is to take the seismogram, make some form of unsupervised learning that is completely data-driven. We will extract features or clusters of events and made also a completely data-driven. And then we will make a regression based on this feature or cluster to see if we can actually predict, model the displacement, the GPS displacement. And so the idea is to use the seismogram, only the seismogram at this stage, and to analyze each window like this one, this period here. And for that, we use the scattering, the deep, what we call the deep scattering network, that is based on the so-called scattering transform. And the idea is how do we, seismologists, know in 1 second, not 1 second, 1 millisecond maybe, our brain knows that this is an earthquake. And we know it for reasons that are associated with both some things that are easy to extract with the classical tool, like the amplitude, like the component, the frequency spectrum, but also with the shape. And typically, here we have this impetus, so we have a strong arrival of P wave, then a form of coda of P wave, and then S wave, and then a long coda. And when we see this, all these things in the same time, we know this is an earthquake. And so it's typically what we want to do. And if we want to do, we can take this seismogram and represent it by a transform that is a wavelet type transform that is multiscale. And the idea that you can take wavelets, a collection of wavelets with different typical time, that is frequency, and we will make a form of convolution of this signal by the wavelet, and it will give us something that we call scalogram, but that is close to a spectrogram. But here the resolution is optimal in time and frequency. And when we have this scalogram, the idea of the scattering network is to take each of these lines corresponding to a particular frequency and to redo this analysis with longer time scale. So not dealing with the change at the very short time scale of the waves arrival, but on the wave shapes of the signal, looking for wavelets going to larger and larger time scale. So, and then, of course, you get, for each of the frequency, you get a new collection of information here. And so you see that the problem is that you start with these things, that you explode into this one, and each line here you explode into this one, and so it's a very multidimensional representation, but very rich in terms of what we can learn from a seismogram. And of course, what we will do is that we will take this type of information and we will make some pooling, that is, that we will consider not the time-by-time value, but we will consider some integration of a max pooling of the coefficient. And so, by the way, what is important is that we have this representation that is interesting because it has some properties that are very positive for us. And so the process that we use is to take the seismogram, the three-component seismogram, compute this scattering transform, this scattering network that give us now a space of features that are the pooled value of the scattering transform. And from all this set of features that are too high dimensionality, it has been already discussed, this problem of the curse of dimensionality, we will reduce the dimension. And to do that, here we use an independent component analysis. That is that we will look for a representation of this space at a smaller dimension, but we add this optimal separation in time of the subspace in order to have this independence of the final features. And so this is what we will use. So this is what we did here, and what we obtained in a sense the extraction of these features that are a time dependent value of a series of amplitude in the optimal direction of the dimensional reduction. So, and from that we can even look at them and see some properties on these features. So what I was willing to show you very rapidly that the typical way of analyzing is now to try to do some clustering. But remember that here we see very well that there are some interesting properties that we can see. For example, here you see that there is a daily trend. That is a good indication that on the nature of this signal. But let's start just with clustering, because if we now perform a clustering based on these results, here we extract 15 clusters, and we can identify the signal in this cluster by looking at the typical seismogram corresponding to the points that are the closer to the centroid of each of these clusters. So from the feature space we go back to the real world, and this is what we see, that this first cluster here actually correspond to glitches. You see, glitches are not only for Mars, we have also some here. Even we have two classes of glitches, because here oh yes, I don't want to compete. But here, for example, you see that double glitches are separated from the single. Then we have here different types. Here, earthquake. Earthquakes belongs to a particular clusters. And you see that we have completely separated the earthquake. We have also sometimes some signal that we do not really understand. But here we have tremors. And we know that this is a good identification because we can compare the tremors occurrence, this cluster occurrence, that is with tremor detection in the same region. So you see that there is a very good correlation between this particular tremor, this particular cluster, and the tremor detection. So it's working very well. And the rest are natural noise, like the oceanic noise, for example. You have the classification is based on a space, representation space, in which you define clusters, okay? And then there is a centroid of the cluster. And so you take the point in this space corresponding to the close to the centroid, that are the characteristic points that define the cluster. And you go back to your data to say, okay, this corresponds to this window and this window. Okay? Okay, so this is what we can do but with cluster. But the limit with cluster is that it's a binary separation. It's a hierarchical clustering. You can choose the level and the distance between the cluster. It's not an optimal number here. It's the number for which, for example, we separate the earthquake from the rest. It was the main reason here to choose this value. But of course, if you continue, if you take the earthquake cluster, you will find a cluster of local earthquake and distant earthquake. So, yeah. Is there a way to, sorry. We have it's completely data driven.
Yeah, I know, but do you supervise at some point just to see if there are false detections or good detections, or if there are
In the cluster? But in the cluster, the problem of clustering is that it's a good question. So I can switch to what I was willing to say. Definition of a good question. And the problem with clustering, it's binary. You are in this cluster or this one. If you are in between, the choice depends on the way you define your cluster. For example, we work at a point with Gaussian mixture. And so it's clear that in a Gaussian mixture, you can be in one with a probability and other one with another probability. And so, but you choose and you put this cluster. It's very binary, so it's really limiting for the analysis, I believe. And this is why I think it's better to use the features themselves in regression. This is what we try to do. It is what we try to do here. Here we try to use this data that correspond to tremor, earthquake, noise, and so on, that are not explicitly expressed, to try to see if they give the information about the GPS. So this is the GPS record that has been corrected from the general trend of the motion, and this is smooth for 30 days here, and this is the displacement rate from this station toward the north in that you can see here. And there are these slow slip events that correspond to this value of negative velocity displacement rate at this station. There is almost 10 years of continuous data that are used here, both for the seismology and for the GPS. So we have the features here that we have seen before, and we use the same, okay, it's what we have seen before with all the details that I forgot to tell. And but I told you that we work with 20 dimension here. So we have 20 features, and this is the smooth features in order to fit with the GPS. But knowing that we have a much better resolution than that with the seismology. But we cannot really test at a smaller time scale. So the idea was to say, okay, let's consider this time series that is the GPS, and then at a point we have to do something. And the simple things we can do is to train a regression, a simple linear regression, and we train it on this period. We took this period here, and we train a regression that is, we can if I have a guess of the GPS displacement just by a linear combination of the features here. And of course, there is an issue that is, for example, how many features do you consider? And if we continue with that, okay, this is the application of this principle. So we learn here, and then we compute from this linear equation that we obtained, we compute the displacement here. So here there is no learning, nothing, and we just try to find what are the regression coefficient on this short time, and you see that we got very good results for the reconstruction of years of GPS displacement. So it is, I think, very positive that say that even in our seismogram, and here again, it's a single station with 3 components, but a single station. Even in this seismogram, you have this information that is somehow coded in a form that we do not really understand, of course, but we know that, for example, the tremor has an importance. So we try to do that, and also you can say, okay, but you use 8 features here. That is a lot. So we can just look at what happens if we try to limit the feature. Oh, just to say, this is the fit of the displacement that we obtain when we use these eight features. But if we limit the features and we stay only with 2 features, we obtain this fit that is the same that you can see here with the contribution of the different features. And you see that we obtain a form of correlation, but it is much less, that indicate that these 2 features that seems to be the most related to the source slip are not enough to completely predict the curve. That means that there are several features, several dimensions that we need in the prediction of the displacement. Yeah.
Among the features that you selected here, you took only the tremors, or you
No. It's it's without clustering. We take the features. Because the features are continuous. It's not a choice of this one or this one and so on. Yes.
Are these features representative of something physical or something?
Well,
Features representative of something physical? Is it like a
yes, it's what you can find is that some features are very related to some physical groups of events. For example, tremors. And but features are very rich information, that much more than cluster in a way, because they are continuous. Because you have cluster and you have trucks passing in the street. The problem is that you have the 2 in the same time. Okay, so at this moment, where are you? you need to have a descriptor that is not binary, that are not telling you, oh, it's a truck, so there is no tremor. You see, so it's why I think it's good to work in this multidimensional feature space and to try to understand. Okay, the defect, but it's maybe not a defect, it's probably the physics, is that a single indication is not enough. That is what we see here, that we need a multidimensional representation in the feature space to capture the GPS data. Meaning that there is not a single seismological indication that is sufficient. Okay? Yes? Because if you take 20, you will find a way to fit. So we test with limiting the numbers and actually increasing the numbers. We see that we need some to reach this type of fit. But maybe the most important result is that when you take only 2, you are very close to the fit, except that you do not reach the right values here, and that could be related to the fact that there are several type of signals, earthquake and tremors, LFEs that are slightly different, and that we do not train at the high value of velocity. So maybe here there is a form of, and it's just a linear, just a linear relation. Okay. Yeah, at this stage, yes. Which probably we can try to learn also, make a form of automatic learning of the. But here, it's just to show that the. Yeah. Yeah. From the
from your features to find best set of your features that fit your tremor catalog.
yeah, the tremor catalog is mostly the cluster number. I don't know.
Yeah, but the interesting question, if you can identify some significant difference in signals between tremor and how you should replace it, because you know that
And I think a part of the answer is the fact that you need several dimensions to explain it. And
no, but you know there is this hypothesis that tremors are more or less equivalent to slow speed, but there is also a question to which extent it's slow. So if there
yeah.
are tremors outside slow,
Yeah.
can you try to address this? Or
We can try to make more analyses of these different features to try to understand more what they describe, and probably try to put more physical argument in the interpretation. And do these type of things. We could, for example, take the cluster and use the feature that correspond to the cluster and try to fit. But it will give you one of two of these one. So, yeah, sorry.
Do you try to train something else in linear regression? Because as I see it, I mean, for the misfit, like three possible explanations. One of them, taking up independent components of features, you call it, or I mean, it could be something that you don't measure with a seismometer at all, or it could be that the linear regression is maybe
No, it's what I said. Probably the linear regression is not enough, and the relation between these different class of events depend on also on the amplitude, for example. That would make sense, because the way you analyze a signal is always a physical signal plus the noise. And the amplitude is a very important issue that is usually left on the side, but all of our records is a mix between several sources, and the relative amplitude is important in the description here. And so it's why also we have to be careful with the linear regression in this story. But probably we can do much more than this simple equation, of course. But this simple equation has a quality to be easily understandable, to see what is the strongest element to explain. Yes, I have to stop. Yeah, no, but I understand. Okay, so as I said, we have to do more to interpret the features, and we could try to learn with full resolution data, that is taking advantage of the extreme resolution of seismology, and to try to go into the noisy geodetic data and to try to get information in this context by using probably artificial intelligence tools too. Thank you. No, at this stage is the windows. I just showed the window in the usual classification type approach. There is no The subtle filtering you are mentioning is something you will find in René Poster.
But you could go through all this
Yeah,
unfolding
yeah,
to also get rid of these other
yes, yes, yeah,
stripped down,
yeah.
let's say,
But yeah, it's exactly what René has shown, that it's possible to do that. Yeah.
so I mean, in the sense you're lucky that you can relate the independent components, you can relate the features to like some sort of ground truth, which for you is displacement. Have you considered a case where you would have features that correspond to some physical process where you essentially didn't measure the ground truth? I mean, you wouldn't have like scales between, let's say, like one feature corresponds to one physical process between
The-
two different
yeah.
components.
But most of the features are describing completely different time patterns. You see the day, night and day, and weeks and weekend, and blah blah, and meteorology, and all these things are in this. There is a strong hypothesis that is made when we say that we use ICA in these things, is that we assume that the geodetic signal are not correlated with the human activity or the precipitation or whatever. And yeah, but we made this hypothesis here. Yeah. Oh, yeah. This is the part that has been trained. This is the part that has been extrapolated. I think it's because you have this impression probably with very rapid changes here, and even at this level, there is likely, it's difficult to say, but likely there is still a noise, a random noise that is still present into the GPS, and all our features are polluted by all the other sources that we have in our seismogram in the same time. So we do not expect to find perfect things at this level. I think what is just a miracle is that with the blind analysis, you are able to do that. So that is that we can trust that there is really a continuous information in the seismogram.